So now let's do some exercise questions. First question is, we need to show that the dimensions of displacement current are that of electric current. So the first one, now the displacement current is given by this formula. This flux can be written like epsilon naught E into area over 4 pi epsilon naught r square over dt. Now, what are the dimensions of all these things? So these are the dimensions. dt has this, so m minus 1 l minus 3 a square a t over l square over t. So once you cancel everything out, you will find that it is equal to a. So this is the dimension of current. Current has dimension a. So the displacement current and the conduction current have same dimensions. In question 2, we have a point charge moving along straight line with some constant velocity. Now consider a small area which is perpendicular to the direction of motion of the charge. Now calculate displacement current through the area when its displacement from the charge is x. Value of x is not large, so that electric field at any instant is essentially given by the Coulomb's law. Second question. So we know that electric field is kq over r square or x square. So epsilon phi e, that is a flux, electric flux is electric field into area, that is kq into a over x square. This is the same thing that we used here. Oh, this should have been q. This should have been q. By mistake I wrote e. Okay, so this is the same formula that we used over in the first question. So ultimately the displacement current will be epsilon naught d phi by dt. So it will be epsilon naught kqa over x square and d by dt. So now let's put all the constant quantities outside. So at the place of k we can write 1 over 4 pi epsilon naught. Then q is also a constant, area is a constant. So ultimately what we will have is x is changing. So we need to differentiate x with time period. So what will happen is that we will have qa over 4 pi and this x will be minus 2x x to the power minus 3 and dx by dt, because x is differentiated with respect to time period. So we know that dx by dt is velocity, so the q into a over 4 pi into 2x, you can also write it like this, minus 2qa and x cube up below, and this dx by dt is velocity v. So this will be the displacement current. In question 3 we have parallel plate capacitor having plate area A and plate separation D joined by battery of EMF E and internal resistance R at t equal to 0. Consider plane surface of area A by 2 parallel to the plates and situated symmetrically between them. We need to find displacement current through this surface as function of time. So we need to find displacement current. So this is the third one. So we know that electric field is Q over 4 pi epsilon naught. Sorry, only epsilon naught A, and this is for the parallel plate capacitor. Okay, so phi will be Q over phi is E into A, so Q over epsilon naught into A, and area this should be, let me write only area here. So area is A by 2, so Q over 2 epsilon naught. So current will be epsilon naught d phi E by dt, displacement current. So epsilon naught d by dt Q over epsilon naught 2 epsilon naught. So now I will be 2 dq by dt. Now this dq by dt can be this is half actually. So half d over dt, at the place of q we can write e c e to the power minus t rc. So it will be half ec minus half minus r 1 by rc e to the power minus tau by rc. So the current will be minus e over 2r e to the power minus td over r epsilon naught lambda. In question 4 we need to consider the previous problem and we need to define displacement resistance of space between plates where V is potential difference between the plates and ID is the displacement current. We need to show that RD varies with time as the given equation. Fourth one, so electric field Q over epsilon naught into A phi E A, that is same Q over epsilon 2 epsilon naught, same as the above one. I naught will be epsilon naught d phi E by dt, so it will be epsilon naught d by dt Q over epsilon naught 2 epsilon naught. So I d will be half dq over dt. So also in simple terms this can be put like this only. So now we need to find the resistance. So it is given to be Rd equal to R e to the power t over tau minus 1. We have to prove this. So to prove this, first displacement resistance will be equal to voltage upon displacement current. Now this voltage can be E minus Id into R over Id. So after simplification, displacement resistance will be epsilon EMF over Id minus R, because Id will get cancelled out. So now let's put the value of Id here. So epsilon, and it will be this value will be used. This value, We can ignore the minus sign if you want only the magnitude. So epsilon over 2r, so 2r will go here, e to the power minus t over rc and minus r. So displacement resistance will be, this epsilon will get cancelled out, 2r e to the power t over rc minus r. So now let's take this r common, so we will have 2e to the power minus 1. Now this rc can be put like tau, so it will be over to tau minus 1. So this will be the resistance. Now this 2 depends on this value. So if we had if we do not have this 2, okay, if we do not have this factor of 2 here, area factor 2, so we would have the resistance equal to rd equal to r e tau over t minus 1. So ultimately the resistance will depend on the area, choice of the area. In question 5, using B equal to mu naught H, we need to find the ratio E naught over H naught for plane electromagnetic wave propagating through vacuum. Also show that it has the dimension of electric resistance. This ratio is universal constant called impedance of free space. So the fifth one, B equal to mu naught H, H will be B over mu naught. Now E naught over H naught, E naught will be B naught over mu naught epsilon naught into C, and H naught will be B naught over mu naught. So it will be 1 over epsilon naught C. So if you put the value, you will find the ratio E naught over H naught. It will be a constant because C is constant, epsilon naught is also constant, so it is a constant. This ratio is a constant and it is called the impedance of free space. It is always a constant, so it is 376.6 ohms or approximately 377 ohms. So this is the impedance of the free space and it is a constant value. Now the dimension of this will be, so dimension will be 1 over epsilon naught C. So what will be the dimension? 1 over the dimensions will be m minus 1 L3 L minus 3 T4 A square, and C is the velocity LT minus 1 meter per second. Okay, so it will give us 1 over m minus 1 L minus 2 T3 A2, and this can be written like m1 L2 T minus 3 A minus 2. So these are the dimensions of resistance. Actually these are the dimensions of resistance. So this proves that the ratio E naught over H naught has a dimension similar to that of resistance. In question 6, the sunlight reaching the earth has maximum electric field of 810 volt per meter. What is the maximum magnetic field in this light? So this is the sixth one. V naught is electric field E naught is 800 volt per meter and B naught is unknown. So we know that B naught is equal to mu naught epsilon naught C into E naught. So B naught will be 4 pi into 10 to the power minus 7 into 8.85 into 10 to the power minus 12 into 3 into 10 to the power 8 into 810. So it will give us 27010.9 into 10 to the power minus 10, or approximately 2.7 into 10 to the power 6 Tesla. So B naught will be approximately 2.7 micro Tesla. In question 7, magnetic field in a plane EM wave is given. We need to find maximum electric field and average energy density corresponding to this field, electric field. So this is the 7th one. B is 200 micro Tesla. This is B naught actually. Sine 4 into 10 to the power 15 per second. This is omega. And T minus X over C. So A part B naught obviously is 200 micro Tesla amplitude or maximum value. So E naught will be C into B naught. So it will be 200 into 10 to the power minus 6 into 3 into 10 to the power 8 into 200 into 10 to the power minus 6. So E naught will come out to be 6 into 10 to the power 4 volt per meter. Then average energy density. So it is half mu naught B naught square. So 200 into 10 to the power minus 6 whole square over 2 into 4 pi into 10 to the power minus 7. So it will give us approximately 1 over 20 pi. So after solving this, it will be 0.0159 or approximately 0.016. So this will be the average energy density. In question 8, we have a laser beam of some intensity. We need to find the amplitudes of electric and magnetic fields. So this is 8th one. Intensity is 2.5 into 10 to the power 14 Weber per meter square or watt per meter square. Then intensity is epsilon naught E naught square into C. So E naught square will be 2I over epsilon naught into C. So E naught ultimately is root 2I over epsilon naught C. So E naught will be equal to 2 into 2.5 into 10 to the power 14 over 8.85 into 10 to the power minus 12 into 3 into 10 to the power 8. So it will be 0.4339 into 10 to the power 9. So E naught will be equal to 4.33 into 10 to the power 8 Newton per Coulomb. In question 9, intensity of sunlight reaching earth is 1380 watt per meter square. Assume this light to be a plane monochromatic wave. We need to find the amplitudes of electric and magnetic fields in this wave. So this is the 9th one. Intensity of wave is half epsilon naught E square C. Now it is 1380, epsilon naught is 8.85 into 10 to the power minus 12. E naught square is to be found out. C is 3 into 10 to the power 8 meters per second. So E naught will be 10.195 into 10 to the power 2. It will be approximately 1.02 into 10 to the power 3. And now E naught is equal to C into B naught. So it will be B naught will be E naught over C. So it will give us 1.02 into 10 to the power 3 over 3 into 10 to the power 8. So B naught will come out to be approximately 3.4 into 10 to the power minus 5 Tesla. So this is how you can find the value of B naught. First find E naught and then by E naught you can find B naught.